Okay, so we can officially start. So, hello everyone. Welcome to episode 79, already 79 of Warsaw Quantum Computing Group Meetups. My name is Pavel and I will be the host and moderator today. And we have pleasure, great speaker, Dr. Jacob Cybulski, who is joining us from Australia. This is one of the reasons why our meeting today is on Saturday and before the noon, because it's already evening in Australia. So Jacob will give a talk about quantum reservoir computing. Just a few announcements before we start. So as you can see, this meeting is recorded. So we are planning to um, publish the video on our YouTube channel. There are no technical issues, of course. And we've agreed with Jacob that there will be a break in the middle of the talk, a dedicated Q&A session at the end, but we'll also try to answer some questions in the middle of the lecture. So if you have any questions, please post your questions on the chat. And when there is a break or later when we have the Q&A session, we'll just try to ask the question, just not to interrupt during the lecture. Um, okay, before we start, we'd also like to thank our strategic partners for supporting this meetup, Sonover R&D, Quantum.io, Onyx, Cogit AIQ Lab, and FinQubit, as well as our honorary partners. So there are plenty of them, as you can see. They all help us advertise the event, spread information, and sometimes recommend the speakers as well. And that's all from my side. So, Jacob, if you are ready, I think we can start, and the Zoom is yours. So, first of all, welcome and thanks for joining us from Australia. It's our pleasure to have you with us this time during the Warsaw Quantum Computing Group meetup. I can tell the participants that Jacob is our longtime collaborator, so he was also a speaker during our recent quantum machine learning conference and was an instructor in the free quantum machine learning workshops that we organized in the last 2 years. And there is a new quantum machine learning workshop coming later this year, most likely in October. So you'll have the opportunity to participate, but today we'll focus on quantum reservoir computing. So Jacob, welcome again, and the Zoom is yours.
Thank you, Pavel, and welcome everybody to my talk. Before I get into it, I will show you my website from which you could get slides for this presentation. So if you go to jacobcybulski.com, you press on presentations, and at the moment, the very top line will be this doc with PDF slides. So you could actually grab them if you wish to. And I actually, I'm in Australia. I formed a small startup quantum company called Enquantit. And if you want to find out more about Enquantit, it's here, enquantit.com. And a lot of work we do is research and training, presentations, and we would like to interact with everybody. Okay, so let's get to the presentation. I will be sitting sideways to the camera because I have a smaller resolution screen where this projection is. So I will switch the camera off for a while, but I'll switch it back on during question time. So in this presentation, I'm going to explain what's quantum reservoir computing. And you can see the small subtitle and the memory duality. So I'm going to talk about our project. The project which was actually started with quantum AI interns. So actually, I need to acknowledge Pavel's contribution to the project because he was running AI interns in 2025, and the Quantum AI Foundation. It was the organization which was overseeing the whole series of projects in the space. And one of those projects was on quantum reservoir computing, and Stanisław Władycza, who is the collaborator on this project, and Sebastian Zions was one of the supervisors of the project. So this wouldn't happen without the AI interns program, which is a great program. So what we're going to do is to talk about a brief introduction to reservoir computing and then move into the quantum implementation of some of those concepts. And later on, I'll start talking about the project itself, the results, and some of the difficulties we face and some of the discoveries we made in the process. So the problem is to do with time series and signal analysis and the reservoir computing. It's a series of models which demonstrated very high very high efficiency of analysis of time series and signals. And so because we've been doing quite a lot of work in time series analysis and developing quantum algorithms for time series analysis, that drew my attention and eventually interest in this space. And classical reservoir computing was greatly successful in many different areas, such as predictions and forecasting, noise reduction, anomaly detection, modeling of chaotic systems. So there's many different applications from astronomical observations, machine condition monitoring, earthquake predictions, and a lot of health-related applications. There is a potential for quantum reservoir computing applications as well as in the same areas. And we actually start exploring this. And there's quite a lot of work done in the space. And I think that our direction is slightly different from others. So what exactly is reservoir computing? And especially for time series and signals. And there are some types of reservoir computing which could be applied to tabular data as well. So classical reservoir computing, I'm going to call it CRC. They're derived from recurrent neural networks, and they are specifically designed for handling temporal data. The key concept is that of a reservoir. And what's a reservoir? It's a large, sparse neural network which is randomly initialized, has fixed weights, and it basically plays the role of a kernel. It shifts the data into high dimensional space in which it's easy to separate your data so it could be handled by simple linear models. Okay, so in classification, of course, is separation of classes. In estimation is basically appropriate clustering and identification of common spaces in the data. Now, one of the interesting concepts in the reservoir is that of an echo. It's basically ability to retain information. So when we show during training and later on during operation data inputs for a period of time, the reservoir is trying to remember that. But at the same time, once the data accumulates, it's trying to gradually forget that data. So there's actually cost of memory leakage. What is the degree of retention versus the forgetting of its memory? That's actually an interesting concept which relates to the way human memory works. What we see on the right-hand side, it's a schematic for the classical reservoir model. And above, you can see there's a variety of different types of classical reservoir models, such as the echo state networks, which relate to that echo or retention of information, with leaky integrator, that means with forgetting. Some are feedback driven, some are liquid state machines, this next generation reservoir computing, time delay, and many, many others. So there's a lot of varieties of reservoir computing models that we could explore. We're going to talk about the simplest one here. What you see on the right-hand side is a typical structure of the model. So we start with initializing the reservoir. That means creating the large structure, populate the structure with random weights and random biases, and then start putting information into it. And one of the key aspects is updating the state of the reservoir. And this update rule, it actually has that leakage rate, which blends new information with old information. And eventually, you blow it up into high resolution, in a high dimensionality of the data, and it's passed to the readout, which is a linear model, usually ridge regression, which is optimized. So there's no other part of the model which is optimized, but the linear regression model, which could be optimized very efficiently. So one great aspect of it is that if it works, we hope it works, but that means that the large neural network, and later on large quantum neural network, does not require the training of its massive neural network. It's only the training happens of the classical model, the small classical model. Now, quantum reservoir model, it's the same structure, the same concept. We are having the state preparation, and it could be quantum state preparation, it could be classical state preparation, then state evolution. Again, we are building a large quantum model, which is randomly initialized with weights and biases. And eventually we are mapping the quantum state into, again, higher dimensionality than the original data, which is passed to the simple classical linear model. And again, the optimization happens only at this end. But of course, for the data to flow through, it has to flow through this massive model in between. You can see with the colors here, I identified here the reservoir state being the key. And where exactly is that reservoir in quantum modeling, depending on the implementation? It could be that all three components will be embedded in a quantum model. It could be that we could start with state preparation classically. We could be evolving classical reservoir model and then maybe just mapping through the quantum model. But the last is what we've done is the locate the quantum complexity in the last stage, the stage responsible for preparation of the features for the small classical model. Okay, so in summary here we will have a quantum reservoir model which will handle echo and fading and leakage. There'll be classical readout model which is the ridge regression. The model will have lots of weights which are sparse and random and fixed, no training required. And the classical readout will be very simple and easy to train. And the great thing about this approach is that since there is no training of the quantum model, which takes a lot of resources, and it's a usually hybrid model, which part of it is operating on a quantum machine and part of it on the classical machine in terms of training of the weights. Here, no training happens, which means that we could very efficiently handle very large data sets. And if you work mostly on the simulator, on your local machine, you would appreciate that because there is no training required. It's very, very fast to handle. I'm going to walk you through our dual memory quantum reservoir model. And I'm going to give you lots of literature at the end. You could actually look for other approaches. The way we're going to tackle the problem of building a reservoir computing model using quantum machine learning is that we're going to build a classical reservoir which will handle the local state, which will allow to blend information into new information into the history of information. And then the quantum reservoir feature map is going to map it into the data which will be consumed by the classical readout. But let me just step away from that. In the majority of reservoir computing models, they take a single input. They then accumulate inputs within the reservoir, and then it produces a single output for the classical readout, or perhaps lots of outputs for classical readout because we're supposed to increase the dimensionality of the single value, which is blended with the history of the previous values which we passed in. So the idea was here, what if we pass more than one value? That's actually being done in other approaches. So the way we work is that we take a time series. For example, it's a chaotic Mackey glass time series. We split it into windows. So we have a sliding window protocol, and we try to predict a single value following that window. It's very simple. Then that window gets passed into the classical reservoir, which has an update rule. The update rule, it tells us at each step, at each window passed in, the reservoir is initialized with zeros, and then each value is weighed with window versus previous history. So the reservoir maintains a state. Usually state at 0 is just zeros. State at step 1 is the previous state. It's multiplied by 1 minus gamma, which is the leakage rate, plus the window coming in by gamma. So the values get multiplied, and we create a new state, which is having part of the memory from the previous step and part of the memory from the window. And so as we progress, you can see each time the state is multiplied by 1 minus gamma, it's slowly forgetting what was at the very beginning, because each time is 1 minus gamma multiplied over and over and over again. And the new value comes fresh with a single value output. So that state is representing in some way the previous values and the current value blended into the state. So each time we're going to run a quantum model, we simply take the state generated. In our case, the state is the width of the window. It gets encoded into the quantum model. The quantum model is executed, and the results, of course, this evolution of its quantum state in Hilbert space, high-dimensional Hilbert space. And eventually, we measure the outcome, and the outcome is measured for each qubit is in 3 projective axes, X, Y, and Z. So we have 3 times as many values as an input. That gets passed to the classical readout, and prediction is made. That's what's happening here. In the middle, I also measure so-called participation ratio, which is derived from principal component analysis. I'll talk about that later, to basically determine what is the dimensionality of data passed to the classical readout. Has it increased from the original window size? Has it decreased? So that's actually an interesting problem. If it increased, it means that the information contained here is actually absorbed a lot of history from the past windows. If it decreased, it probably means that it shrunk the information passed to the classical readout. So that's more or less what's happening in the dual memory quantum reservoir computing. And why dual memory? You'll see that when it's in action, but we have the short memory represented by window and the long memory represented by the history of the previous input passed into the reservoir. This is the way the reservoir feature map looks like, which is the structure of the quantum model. And I'm going to explain that a little bit. We have 2 different alternative implementations here. One is based on ZZ feature map, and another one is on angle encoding using a rotational gate on X. One is much longer and one is much shorter. Okay, so why have LXXIX ZZ feature map? It's actually Qiskit style of encoding. In Pendulane, which we use for the majority of our simulations, we were also trying the so-called IQP encoding, which is native to Pendulane. And it differs in a mathematical expression, very similar. But ZZ feature map, as offered in Qiskit, they're much more superior when it comes to encoding data for the reservoir. This is the mathematics of it. It has got two components. One is the first order input terms, we included biases here as well imposed on input, and the second order terms in which the data which is flowing through is um, rotated around the value of pi. And that actually gives us interesting phenomenon. It warps the manifold on which this model is going to live and evolve in Hilbert space. And the warping is very severe. So it means that the data gets spread around and in the curved multidimensional space. And that actually offers some advantages against angle encoding, in which it's only linear transformation happening. In angle encoding, the data is not correlated before it enters the Hilbert space. And basically, it doesn't offer any quantum advantage in the long term, especially with the model which is not trained at all. So we didn't have a lot of luck with angle encoding, but we could get some decent results with angle encoding. Also in penny-lane IQP encoding, because there is the terms are not reversed in phase encoding. That means it's a simple product. It doesn't offer such warping effect as it is with Qiskit style of ZZ feature map or LXXIX ZZ feature maps. Now, in this model, there is also another feature. We are actually actively re-uploading the data in the middle. So the data from input is, first of all, input is prepared in phase using ZZ feature map, and then it's re-uploaded using angle encoding technique, which means it's providing additional warping into in the manifold in Hilbert space. Now, there is a lot of parameters here. There is a lot of biases, and also the phase information, which is the data is encoded in phase. They can be manipulated. There's a lot of dimensionality, a lot of hyperparameters, and we thought to start grouping them for later analysis. So we coined the term structural complexity of that model, which basically is number of qubits times number of layers. That sort of gives us the dimensionality of that circuit. But also it's a proxy measure for the number of parameters, which normally would be trainable parameters in this model. We also have the hyperscale magnitude. We are scaling the weights, we are scaling biases, we're scaling the phase encoding as well. And we experimented with different level of scaling, and that has tremendous impact on the result, especially in this highly warped multidimensional manifold. So I'll talk about the sensitivity of the encoding, the sensitivity of the model later on. So this is just to bring issues that will appear later on and show you that it was a lot of thought put into it and a lot of experimentation with different encoding schemes in different ansatz design, and eventually also with the measurements. The measurements here are simple expectation values projected into different axes. So we gain only dimensionality 3 times. We experimented with probability interpretation of measurements, which give you exponential space of parameters on output, and it was too much to handle. So we stayed with that 3 times number of qubits. The number of qubits is the length of the window. So to bring it all together, this is the mathematical expression of that reservoir. Here's the input versus windows, the leakage rate, which is the rule of the reservoir, different encoding blocks. We decided to stay with ZZ feature map, the Fachhavlicek-Kiskit-style ZZ feature map, and use the quantum reservoir as the reservoir quantum feature map, which has two components, the encoding component first, and then the reservoir component, which is the ansatz. And the final ansatz state is 3 times number of measurements, or number of qubits as measurements. And the readout layer is a standard ridge regression model, which is being optimized using regularized mean square error as a cost function. Okay, we're going to discuss where does it come from. It's obviously did not come from anywhere. It's a lot of work was done by other people in this space. Here at the top, I list many different approaches which are currently available in literature. We have ESN, which is eco-state network with leaky integrator by Jaeger, next generation reservoir computing, Gauthier, time delay, QRCs or ARCs by Appellant, liquid state machines by Mass, physical reservoir computing. This is a good summary by Stepney, and extreme learning machines by Huang, which actually work not only with time series but also with tabular data. And we have increasing number of approaches applying quantum machine learning to this space. The most well-known is probably work by Kobayashi, the feedback-driven quantum reservoir computing, and dissipative reservoir computing. There's some attempts to do multivariate predictions, and we have quantum extreme learning machines as well. So a lot of work before. I selected only the ones which had greatest impact on what we've done. And of course, the work by Jaeger is fundamental here. First of all, is the whole concept of eco-state network is the key concept. When I say eco, just remember this is to do with memory retention. It is responsible for our long and short-term memory. And in his implementation, he worked with one input at the time, and the leakage was controlling only internal state decay. And the flow of information was from input through leaking temporal blending as we do it, the recurrent state update as we do it, and the readout. Okay, so that is the foundation concept by Jaeger. Maas, who created liquid state machines, I think the main idea in what he proposed is that reservoirs don't need to be continuous network or continuous models. They could be very sparse. So sparse reservoirs are quite sufficient for effective execution. In Appellant's work, who actually was designing reservoir computing for photonic machines, he introduced the concept. He worked with the concept of restructuring the way the reservoir computing could work. So basically, he used a single nonlinear node, which was multiplexed in a time domain using delay loops. And from a single generator, he developed the concept of the whole reservoir machine. So basically, that the work provided some foundation how we are going to deal with temporal relationships in the best way, rather than simply relying on original Jaeger and Maas work. Can we redo it in some other ways? That's why we try to combine the sliding window protocol with the eco-state machines and combine those two concepts. It didn't look like a breakthrough, but we had some interesting results. And eventually got here, the next generation reservoir computing. It's another great idea. Basically, forget the neural networks. We could actually work with high dimensional polynomial feature maps. Okay, so it could be tabular data, it could be linear algebra, simple multiplications, and that actually is very, very tempting. Yeah, we don't have to worry about neural networks and networks of any kind, especially with their sparse. We could go straight into the concept of feature mapping to replace random networks. That's exactly what we adopted. And interesting is that he uses time series windows as well. However, his model had no internal reservoir, no long short-term memory balance, and the polynomial combinations would explore combinatorially, which would be high complexity you had to deal with. But good thinking. Finally, Stepney physical reservoir computing models. Because the weights are never trained, any other complex physical system could act as a reservoir which is randomly generated large model. And people play with optical cavities, spintronic oscillators, buckets of water waves, and many others, which could simulate random behavior, which could give us the interesting model as a result. But we will not be focusing on that, just to mention that there's a lot of work done in this space. And eventually, the dual memory quantum reservoir computing, which we are presenting here, it adopts the leaky eco-state network as the temporary memory. Quantum feature map is used for high-dimensional mapping and temporal spatialization. Okay, I never mentioned this before, but I'll go back to the previous picture here. When we get snippets of the time series, the windows, the window, when it enters into the system, it is representing time, points in time, measurements in time. When it actually goes through the classical eco-state machine, that's already upset because it's blending with the past. When it goes through the quantum reservoir feature map, we'll start losing the relationships between points in time. But what we try to do is to retain relationships between correlated points in time. And that's what's happening here in high-dimensional Hilbert space. But what we get here, this is no longer points in time. This is actually some kind of a representation of the state of the quantum reservoir feature map. And it's no longer time. It's correlated, all the data points are correlated, but they are in space rather than in time. So that's why we call it, the whole process spatializes time into space. At this point, a good question would be, why quantum? Does it have to be quantum reservoir? Why not sticking with neural networks? Of course, we just wanted to do quantum. That's a good enough, for us, was a good enough motivation. But let's defend it in some way. So we look at it from the point of view of the geometry in multidimensional space. And there's a lot of similarities between classical neural networks and quantum neural networks. The fundamental difference is the nature of the space. We have Euclidean space when it comes to neural networks. We have a complex projective space in Hilbert space. The space, Hilbert space, is warped by equivalence relationships. That means that's the relationship which comes from the global phase invariance. Euclidean space is also warped by activation functions. And equivalence relation in this context is the scale invariance in ReLU nets. The second most important way, oops, I just moved things. The second most important thing is the way we measure distances. Okay, in Euclidean space, we measure distances in Euclidean measurement. In Fubini, so Fubini study is a measurement which is based on similarity of quantum states. So this is very different already here, and that completely changes the way we measure similarities and distances in a Hilbert space. Information geometry, as given by gradients, Fisher information matrix. In classical context, in quantum, we have quantum Fisher information matrix, very similar concept. So similarities, the main key idea is that in quantum reservoir, we have a very different geometric mechanism. We have exponentially vast Hilbert space as opposed to classical neural networks. We have heavily warped manifolds, which of course, they could be compared to Euclidean warping, but they are much more flexible. And basically, we need to rely on phase as the key force, which is shaping the space in the multidimensional space, in the Hilbert space. Okay, so let's get into, I think we start talking about our model. First of all, are there any questions so far? So let me just look at where am I? All right, things are hiding from me. They are, how do I find our chat? Okay. Good chat. Okay, that's probably not for me.
Yeah,
So
There's a lot
excuse
of
me,
questions.
can I
yes,
propose
yes.
to open
Sorry.
the audio and the video both for the discussion?
Yes, this is okay. So if you want, you can also raise your hand and
I mean,
unmute and ask a
with
question. If you,
both video and audio on.
so we record everything. We record both the video and the audio. If you're asking about the recording, but I'm not sure. Or okay. Anyway, Jacob, I think we're ready
Okay.
to answer some questions, right?
Okay, so I can see lots of questions here.
Yes, there are a lot of
Okay.
questions, but so there is one question from Magdi. Oh, sorry, several questions from Magdi. Can reservoir computing be used in problems other than time series or regression tasks?
Well, if you have, I mentioned that reservoir computing is mainly for time series. I cannot see why not, but I think that you lose some aspects of reservoir computing. It can be used for tabular data. You could always see what happens, but there is also this other model, which is extreme learning machine, which is designed for arbitrary type of data on input.
Okay. Can we say reservoir computing is kind of recurrent neural network or LSTM? Oh, okay. This is not okay, but please answer, Jacob.
Okay. Is it okay? Reservoir computing is not RNN or LSTM in general. I mean, it's there's a lot of implementations based around RNNs, but I think that it abandons that concept very soon because once you get into a very large network, there is no training involved in that. So I don't know how you could actually do it with LSTM or RNN without training. Okay.
Okay. I think it's fair enough. There's
Yeah.
another question from Magdi. Imagine the number of features is around 1000. If we use angle encoding or feature maps, then do we need to reduce the dimension to be compatible with the simulator or hardware? If I'm correct, then what is the best method for dimension reduction?
Okay, so that's actually it's not just for quantum simulations. It's a common problem with time series analysis when you have thousands of features. But when it says features, you mean the features moving in time, yes? So like a picture or genetic profile. I think you're going to struggle with quantum machines nowadays. You need to reduce it somehow. You could compress your features in using a variety of different techniques for feature compression. You could also do, you could perform some chi-square feature prioritization to determine which features are most relevant to your task. So I think that it's a common problem. You need to reduce your dimensionality to be able to work with quantum machines or even with classical ones. Okay.
Okay.
Yeah.
Yes. Yeah, there were some comments, and let's see. Yeah, there are some comments from Sebastian. Yeah, there's another question from Magdi. If we use some methods such as autoencoder, then why not using the neural network at all? And what's the benefit of using reservoir computing? I mean, is there any benefit regarding the execution time necessarily?
It's the speed. There's no need to train it. So the reservoir computing, the great part of it is that you don't need to train your neural network. Okay, so that's the key thing, which means that instead of, especially for quantum reservoir computing, you could train your model completely in 1 hour rather than several days. So on a simulator, on your machine, on your desktop. But of course, there is nothing stopping us to use artificial neural networks and stay with them. And it's a good idea to compare the performance of the two, which I've done, and I'll show it to you in a minute.
Okay. There's another question from another person, from Eamon. Is it possible to use a quantum walk for encoding quantum reservoir features?
Is it possible to use what? Sorry?
To use a quantum walk. I believe
Oh,
that this
quantum
is
walk.
quantum random walk, I believe.
Yeah, it's a stochastic. Oh, sorry, it's a quantum technique. I don't know. I think it's a very different concept. I'm not sure if it's applicable to things like prediction, forecasting, that type of task. Quantum walk is definitely useful for finding the average behavior somewhere. So if you want to um, estimate your futures of the stock market, and you want to look at every single um, uh, possible combination of behaviors from today until month in the future. And I think quantum walk is definitely very effective in that to find the expected value at the end. But I'm not sure if it's good for forecasting in general or prediction of the precise value.
Okay, there's another question. Do you encode the reservoir state into quantum state?
Yes. So that's actually, so in our implementation, we have um, classical reservoir, and that classical reservoir is generating the state, which is then encoded into the quantum feature map.
Okay. There's another question. Could it be possible that the quantum reservoir itself holds the long-term memory and we could discard the classical reservoir step?
Yeah, so that's actually an interesting question because I played with that and I was actually trying. First of all, you need to remember that the quantum model itself has no memory. Okay, the quantum model executes and finishes. So you need to be able to have some kind of a feedback loop. So you could take the output and feed it back in, or have some kind of a repetition happening. So there's actually a lot of work in this space. So you could actually implement avoid having classical reservoir and have only quantum models themselves, which keep either within the structure or within the feedback, the previous state of the model. Yeah, so that is actually what people do.
Okay. There's another question. Then, is there a reason for using quantum reservoir computing explicitly? I believe that the
Um,
question is about the advantages of
yeah,
quantum reservoir computing.
yeah. Well, I think that what we get from our quantum, whoops, why can't I'm moving forward, I can't go back. Okay. Okay, so the quantum So there is actually a number of things. Number one is that you could actually generate high-dimensional space very quickly with a quantum model. So the Hilbert space is exponentially large quantum space of states, and this is the state you want to represent in there. Number two, we work with um, the manifold. Manifold is the representation of your model state in high-dimensional space, and this is a very complex state. It combines lots of substates, and it has a shape, and that shape determines distribution of your data on it, and that shape also helps you to determine like separation of groups of data in time. Now, I think that the classical neural networks work differently. They're feature evolution networks. So they have layers and layers of features which first get blown up into bits and then get reconstituted layer by layer until you have a desired effect on output. So I think that the problem is different because with quantum models, you try to solve most of your problem in that exponentially large quantum space rather than moving in small steps, trying to move and evolve features. Here we evolve states. There's similarities. So I think that I'm not sure if there is you can't say that quantum will be better or one will be better. It's probably a good idea to see which one performs better for the task.
All right. Good. There's another question. Could you please explain why you use variation quantum algorithms for quantum reservoir computing as showing in the beginning? The VQA uses gradient descent while QRC uses closed form equation.
It's probably you're probably right. I was actually thinking about it today. Okay. Um, should I call it the VQA or not? It probably depends what type of reservoir you're implementing. So there could be part of that reservoir, it could be training, could be completely untrained. So I thought I'll leave it in because you need to have some way of determining what should be the weights, what part of your quantum solution. So you could actually have part of the quantum model to be fixed and part of it could be trained, for example. You don't need to have a classical readout at all. You could have one large model in which part of the model is fixed weights and part of the model are trainable weights. That's why I thought I'll leave it here as a VQA because it gives us this flexibility for different approaches to creating the reservoir.
Okay, good. All right. I think that we've answered all the questions on the chat, or maybe there were so many comments, so it's possible that we missed something. Would someone like to unmute and ask a question, maybe? Last chance.
Okay,
There will
we
be a
have another.
dedicated, there will be a dedicated
Yeah.
Q&A session at the end. So let's continue, Jacob, please. Thank you.
A few qubits give you a huge Hilbert space. Yeah, they do. Yes. Well, Sebastian. Yep. Okay. So let me just show you some of the results and some of the examples of the difference, for example, in using different encoding scheme. So what you see on this slide is we have exactly the same data, the same structure of the model, the same hyperparameters, except for the difference is the encoding type. So we have here angle encoded data. This is the mean square error in relationship to the leakage rate. Okay. For training, the blue, and testing. Okay. Here we have the Pendeline style IQP embedding, which is also ZZ feature map. It's very similar to what you see in a simple angle encoding. And here we have the ZZ feature map, the Qiskit style feature map, you can see the nonlinearity. So suddenly the leakage rate versus MSE, we have a huge volatile bending of those curves. Some of you who may be keen, have a sharp eye, you can see that in this particular case, with this structure, ZZ feature map performs worst. So it has the highest test error, and the best is, I think, 6 is this one, which is IQP. And that's the reason is that I picked severe, high scaling of the phase, 0.5 instead of 0.1, where is the nonlinearity is most pronounced. And just to show you the difference in the way they operate. Okay, so ZZ feature map give you huge nonlinearity. It's easy to spot your minimum and the maximum, and the behavior is highly nonlinear, which means it's very sensitive to its operational parameters, which means that you need to do a lot of experimentation to pick the optimum. Okay, so I think that gives us the feel of what will happen with the reservoir where we employ ZZ feature map. We have a lot of warping in the Hilbert space. It's reflected in the results of its operations. The second aspect is, okay, and I probably should have mentioned here that it's also sensitive to things which are listed here, like number of qubits, number of layers, the scaling of weights, scaling of biases, and scaling of the phase. In fact, if the phase scaling is 0.1, it will look very much similar to IQP embedding. Okay, what also happens is that like any quantum model is highly sensitive to initialization of weights and biases. And so here I have 11 instances of the same model. Each instance is differently initialized. And you can see that result of leakage versus mean square error. You can see the shadows behind here, a shadow in red. It shows you the boundary of different behaviors of different curves within that band. The same with training data. You can say the training curve is even worse. For high leakage rates, it's actually fanning out. So what it means is that you can't simply rely on your luck. You can't simply run it once and hope that that will give you the right answer. So you need to actually do several instances and perhaps get either median performing model or get the mean outcome from those models. So here we have the mean line, the mean square, and that's what we do. We have 11 instances per model. And because that actually leads to experimental framework for this project. We are varying here number of qubits, like 2, 4, 6, 8. We vary number of layers, which was 2, 4, 6. We vary number of leakage rates. There's about 13 leakage rates. And we vary also weights and biases and phase and other things. So if we look at all the variants, we have 3,240 different architectural different quantum reservoir computing models. And because we compare them against very similar classical models, there's additional 720 models. Each one of them is run 11 times, different instances. So we're talking about 32,000 models for each data set. We have 6 data sets. There's a lot of, okay, I think that I made a mistake here. We have 261 model instances times 6. We have 1,200,000 models that we ran for this project. Okay, so why is it possible? Because we work with reservoir computing. We don't train those models. If we had to train them, this would be impossible. And that was running on a simulator on my gaming machine. Okay, so the scale of this project is quite large, and we're also playing with different encoding schemes. In this particular case, we use some variant of Qiskit ZZ feature map as well. So we may need to do more. What is the type of data we used in our experiments? We tried to use the worst case scenario, and we used the chaotic data generators. We used 4 of them or 3 of them. Mackie glass, continuous time delayed chaos generated. NARMA, it's a discrete time nonlinear stochastic process. And ARMA, linear stochastic process. And we fixed some of the parameters, and we had different results. So we have one is Mackie glass tau 17, looks very much reoccurring. It's smooth and repeating pattern. And then varying tau value, we get more and more chaos. We have NARMA. NARMA is characteristic because it looks into the past few steps to determine what should be the next step with the noise. So this is NARMA 5 and this is NARMA 10. NARMA 10 requires looking at 10 steps before. And ARMA, which is quite chaotic. So we try to figure it out by looking at them. We can see how much chaos it is, but we try to formalize the level of chaos using different metrics as Lyapunov exponent, measurements, a rate of divergence, correlation dimension, fractal spatial complexity, permutation entropy for ordinal dynamics information. So using those 3, we try to assess the level of chaos that our models have to deal with. And here is the 6 data sets and models which we generated for each. So what you see here is it's a plot, quite unreadable perhaps. It's a plot where every bubble is a single model, 11 instances. And the size of the bubble indicates its complexity, which is qubits times layers. The color indicates the leakage rate, which that model adopted. And what else we have? The location, vertical location is participation rate, which is a measurement derived from PCA, principal component analysis. It basically says how many principal components are being used for that model. So it tells you how many components, dimensionality, the model actually embeds in the data. And the mean square error is more to the left, indicates the better the model. The leaf triangle indicates the best classical model, which always is somewhere there. And I have a pointer to a good model, the best quantum model. And you can see that with the less chaos in data, the better classical models were performing. With more chaos, suddenly quantum reservoir was performing better than quantum reservoir on different aspects. But looking at the bubbles is not going to make you any smarter. So let's look at the way we analyze this data. So starting with example, which is Mackie glass tau 30, which is this distribution of models. You can see we have here a number of rectangles, which are basically, we split the mean test mean square error into segments. Because there's a lot of a concentration of models somewhere in the middle and fewer on the edges. And the same thing in vertical domain. So we try to create regions of more or less the same number of models in them. And then we color-coded them depending on the leakage rate. The brown means that the model is high leakage rate. It simply looks at the window and ignores the history, the memory. Blue means it's actually actively looking at the history and not so much on the current window. And somewhere in between is it uses the balance of both. The little diamond, pink diamond, it gives you the optimum classical model. And the little round yellow dot, it shows the optimal quantum reservoir model. And here they have they're the best models of all. They have very similar performance, and the classical model is slightly better. There are two models which, for this data, they completely ignore the reservoir. They just focus on the current window blown up into a higher dimension. The second chart is actually supporting this one. It actually tells us what is the size, the structural complexity, which is qubits times layer of the models. And what we can see here is that the largest models, they are very poor performance and they retain a lot of dimensionality. So they don't perform well. It seems that the optimum models seem to be squashed in between the smallest models with the smallest dimensionality. So that's actually interesting, that the models don't completely ignore the history, the past memory. They focus on what's in front of them and they perform well. But that is telling us something about the data. This Mackey glass is highly predictable. So those models have no problems dealing with them. What you see below is actually another revealing aspect of this analysis. Based on the parameters of each of my dot, I identify the structural complexity precisely, which is number of qubits times number of layers, which is that column. And I know its scaling factors, which were used for this run. And that actually gives us the performance, okay, of that model. Its corresponding variance is in this table. So what happens is the quantum model performed well. It performed as good as the classical model, but the coloring of this cell indicates this high variance across different leakage rates. So if you were to consider what is the best leakage rate for that model, you would have real difficulties to choose between. There's a lot of volatility in that plot in this particular segment. So that's not the best model to choose from for practical reasons. Is perhaps we should be looking at something not as good, but more predictable. Now, this is NARMA. That's actually the most interesting analysis. NARMA 10, we require the generator, it looked at 10 values before to generate the data point, which means that ideally, if you want to fully know what's happening in that signal, you want to have a window of 10. But it seems that the best model was quantum model, and it was very small model. It's a model which was structural complexity only 4. So it means either 2 qubits by 2 layers. Probably that's the one. So it's a very, very tiny model. And that model is highly stable. The variance is minimum. What it means is also the color of that. He said the leakage rate is 0.5. It relies actively on both the memory and the current window. So it has a lot of information condensed into that input to the classical readout. And the performance shows that. So that's actually interesting. The QRC combines reservoir memory with the window, maps it into high-dimensional warp-field space manifold to recognize patterns longer than the window size. Okay, so that actually, it's interesting. That's also a reservoir model. This is the classical reservoir model, which it behaves in a very similar way, but uses just the normal neural network. Okay, so in this particular context is a loser. And his AMA model, which has very similar structure to this one. So one more thing to notice here is that you can see the models which take advantage of the reservoir. So we have the whole block of them, blue areas, and the models which don't use here the classical model not only was worse when it comes, well, a little bit worse. So it's actually pretty good. But again, the quantum model gives us good result, and it's a highly stable model in its class. The quantum model really takes advantage of its memory and the window, the short-term and long-term memory. The classical model is not using that memory so effectively, so it's got much higher leakage rate. It's probably is struggling with the volatility of the signal, and at some point is trying to simply look at the window rather than memory, because the volatility in data means volatility in history and volatility in phase in the quantum space. So some reflections on experiments. First of all, when we use that feature map for encoding data, in phase-encoded quantum systems, information is not stored in just amplitude. It's embedded in high-dimensional interference of states in the quantum space. Okay, so we need to keep it in mind that it's not the amplitude. It's a much more complex information distribution in Hilbert space. The phase information is notoriously sensitive, and because we're dealing with volatile input sequence, such as those used in experiments, each new time step applies completely different, heavily warped phase shift to the system. So if the leakage rate is low, the quantum state tries to hold on to the previous states. If the leakage rate is high, basically it ignores completely the past memory. Okay. The optimum quantum reservoir computing models are not necessarily linked to high dimensions. As we can see, is that the best models had high dimensionality as measured with the participation ratio. So that's actually interesting, is small models perform, small reservoir models perform well. The optimum quantum reservoir models are outliers in the class. Well, when you think about it, if you try to optimize the model, and it's hard, and eventually you find the optimal model, that means that model is unique amongst the models surrounding it. And that's actually what's reflecting here. Quite often we get the best model in a group which doesn't belong to the group. Okay, it's there for whatever reason we decided to classify it amongst them, but it has slightly different set of parameters. So it's usually an outlier in terms of participation ratio, the hyperscale magnitude, structural complexity, and of course the performance, because it performs best. And a few remarks on ZZ feature maps. It is vital for an optimized reservoir setting. So since the model itself cannot be trained, we can't rely really too much on the classical readout. It means that something has to substitute the training, and the substitution for training is, in terms of the quantum models, is the shape of that manifold in Hilbert space. And so when you pick something which shapes and deforms the quantum space severely in organized fashion, which maintains the correlations between substates, that will probably be a good substitute for training. And that's what we find with ZZ feature map, where the coordinate transformation, it acts as hard-coded geometric optimizer. So that's actually an interesting observation here. Angle encoding, we wrote a paper with Sebastian, which looks at simple encoding schemes. They don't offer any quantum advantage because of the linear scaling of the states. IQP encoding, it's an encoding scheme which was designed for scientific simulation, which really rely on linear transformations. And They are predictable and tunable, but they don't have that sharp, uh, nonlinearity in Hilbert space. And of course, the Cybulski ZZ encoding proved to be the winner in amongst those. So that takes us to the reflection and summary about reservoir computing. We learned what they are, the classical ones. The key concept is that of a reservoir. Another key concept is that of leakage or memory loss. So memory retention, the echo, and the memory loss fading is the leakage. And they are successful in many different applications. When it comes to our model, hasn't tested yet, but we're still exploring it. The future applications are many. There are many types of classical quantum reservoir models from which we borrowed ideas. And currently, the project focuses on the best quantum reservoir architecture, which could demonstrate the dual memory system for short and long-term retention. And that's why we called it dual memory QRC. Some reflections about the shape geometry of Hilbert space to accommodate what happens there, how the data is projected into multidimensional Hilbert space. And that's actually key for the reservoir, which is not being trained. So you need to project it in a way that will help the classical readout later on. When it comes to experiments, we talked about ZZ feature map as the best way to approach it. The Qiskit way, okay, not the Pendelane way. They're quite effective and competing well with classical reservoir models, at least the ones we implemented. And they show the performance best on data which is chaotic, and the patterns are very long-term patterns. And so the long-term patterns could be captured by the reservoir, whether classical or quantum. And another interesting observation is that it's the small models which seem to perform best, not the large models. And we tend to go in quantum machine learning to develop very large models. And maybe that's not necessary, especially that you need to have huge resources for training. What you find is there's a lot of literature here for you. And if you do a few steps further, you don't have that, but you have the results of other experiments which we've done. And here I show you our classical reservoir model, which is explained in a similar mathematical way. And it's actually very similar architecture to the quantum one. In this point, thank you. I'll come back to questions. I'm sure you have a lot of questions.
Yes, indeed. Thank you. Thanks, Jacob. Let's come back to the questions. All right. Yes. Let's go back. There are some new questions coming. Okay, so I think that the next question was from Sebastian. Can we see reservoir computing as a special time embedding of our data to a very special random generator curved Hilbert space?
Sorry, I didn't get it.
Sebastian, maybe you can unmute and ask. I can read it again. Can we see reservoir computing as a special time embedding of our data to a very special random generator curved Hilbert space?
Probably. It's
Not easy.
I think that's how you got it. It is. I think that what's missing is that memory in the middle, because I think it's less to do with the structure and more with the behavior of it. So you see, the reservoir is it's a functionality of it rather than storage. So if you say it's a reservoir, quantum reservoir computing is some kind of a schematic structure. I agree with that. Yes, we have random generated network and we have data on input. What's missing is that blending of current information with the past information repeatedly. So that blending, because of the penalty that um, leakage rate is penalizing previous states from step to step. So there's a more and more severe penalty imposed on states which are far away into the past. And I think that's the key, that state could be actually captured in small amount of information which is embedded in that window size the window size snippets of information and then passed on. And then the quantum model, the map is actually blowing it up into multidimensional space and trying to find the correlations between them via entanglements of the model. So that's actually the functional aspect of the model, which we tend to miss and look at it only as a structure. Okay. Any more questions?
Yes.
I think,
Can you hear me?
yeah, I can hear you.
So yeah, the next question could be my question.
Yeah.
So as you show that you encode the reservoir state into the quantum state, right? And
Yeah.
did you encode it in sequence?
Yeah.
So you encode
Well,
the
okay.
so
So
the
what
time
happened?
T1, and then do you add the time T2 in the same circuit, right? And then
Okay.
in
So what?
sequence.
Okay. So what happens is that the quantum reservoir feature map, it receives only the current state from the reservoir. Okay. So it receives just the data, the size of the window. But that window, it encapsulates logically the previous states and the current state. Okay, so it's basically every value in that window, it undergoes that transformation. So the previous state, which is like a window, it's a state which is on a window size. It's we have a leakage rate multiplication of it from the previous state, plus we have the values of the current window combined together. Okay, so we are actually changing what's coming into that reservoir. We do some mathematics on it, very simple mathematics, and that's the state is passed in. So you think, yeah, we're not passing the entire reservoir in, we just passed one state at a time.
One state, one window state, you mean?
Yeah, so the state, because we passed one window in, we calculate the state gets passed in, and then it's blown up into the new representation and passed to classical readout. And of
Okay,
course,
so
we do it, that's a whole window.
okay, so how many time step that you use? Because otherwise we will increase the number of layer, the depth, I mean.
Well, we have as many layers as you design. Okay, so
Okay.
it looked like the best models had very few layers and very few qubits.
Okay.
So, and the prediction was high. So
Yeah.
I think the transformation of that classical state, which does the trick. And of course, because it's time series, so we get window after window after window. So we actually get, initially, the classical reader is going to perform poorly because we start with zeros as a starting point. And only after time, so it needs some warm up. So usually the reservoir initially has terrible
Yeah.
performance, and then it starts performing well. Okay, it works a little bit like like a neural network, which has LSTM. Okay, so you feed one value at a time, but LSTM's got the buffer of values inside. Yes, but the quantum models cannot actually have that unless you modify the structure of the quantum circuit.
Okay, thank you.
Mhm. Any more questions? Okay. Thank you for your good words about the slides. The slides are
Jacob?
there. Yeah.
Yes, okay. Oh, there was a question about side because I wanted to ask another question
Mhm.
from Mehdi. Okay, it was asked earlier, I think. Imagine we use a simulator. Is there any relationship between the number of qubits and the execution time? I think it's more general, not related to
Yes, they
the.
are. Yeah.
Hmm.
I mean, look, so here I have, because we tested lots of models, okay, of different size. Okay. So you can see that we have models, the complexity, which is number of qubits times number of layers, is 48. Okay, so the largest was 8 qubits and 6 layers. And the layers themselves, they had each qubit had 3 parameters. And so that's times 140 something parameters. And if you consider also input parameters with ZZ feature map, and we also have every layer we have re-uploaded inputs. So there's actually a lot of parameters there. There's probably a few hundred parameters. So if you try to train it a normal way, try to find the best possible optimal model for the data, that will take you some time. And that will take hours or days to train it, depending how fast is your machine. If you work in a laptop, it takes you days. I trained here all the models. I think that one model per day. One data set per day, or maybe 4 hours on my desktop computer. So 332,000. What was the measurement? What was the calculation? I have a calculation somewhere there. Okay, so we have here 261,000 model instances per. Okay, so that's how many models I would train in 4 hours. That's very fast. Okay, so I'm training only the small linear model. Okay, everything else is random. So that's the beauty of this approach. It still gives you good results. That's the amazing thing is that you would think, yeah, let's create a neural network that doesn't need to be trained, just populated randomly, and it actually gives you results. So that's actually a big conceptual step. It really relies on the dimensionality that we blow up. It's like a kernel. So if you use kernel methods, you get the same result, except that with kernel methods, classical kernel methods, you need to know what kernel function is suitable for your data. So there's about 16 different kernel functions. You need to pick one and be lucky. Whereas here we don't worry about it because we rely on high dimensionality of Hilbert space that will blow up into high dimensions even higher. Okay, so that's the beautiful thing. Digital bit or bit. Hang on, what is you referring to? Across time and space? Yeah, not sure what you mean. I don't think I use say the word bit. Maybe, to bit. Yes, it will blow up to bits. Yes. I just say things, but I don't think. Okay. So hopefully that gives you some idea what you can do with reservoir computing, whether classical or quantum. I actually was fascinated by this. There's so many different types, and each one is working slightly differently. So it's a lot of reading. The reading is quite mathematical if you look at academic publications. The math is not. Quantum papers are challenging. The classical papers are easier to work with. Once you see one and understand one, you probably understand all of them. Okay, so because there's a lot of repetitions. They all rely on the same mathematics. But the programs are simple. Okay, so if you go to some sites which do tutorials of different algorithms, they're easy to follow.
All right. Thank you. Thanks,
Thank you
Jacob.
so much.
Thanks.
Okay.
So thanks everyone for coming. So before we finish, I would also like to present some final slides, just to invite you to our next meetup and give some useful links. All right. Okay. Hope you can see my screen again. So we'd like to thank Jacob again for this great
Thank you.
lecture and patiently answering all the questions. And there were many comments. I'm really happy that people were such engaged in this talk. So if you are interested, you can stay in contact. So here, this QR code will lead you to the website with all the links to our social media profiles, Discord server, newsletter, mailing list, and so on. So I would just leave it for a few seconds if you want. And of course, it is recorded, so it will be also available on the final video recording, hopefully. We would like to thank our strategic partners again, Sonovero R&D, Quantum.io, Onyx, Cogit, QLab, and FinQubit. And we thank our honorary partners as well. If you are interested, you can also donate our activities, especially if you are in Poland, you can donate a portion of your taxes for our statutory goals to help out organize even better events in the future. And last but not least, we already invite you to the next episode. We do not have the exact title yet, but we know that there will be a speaker from Quantum.io, which is a Polish startup working on quantum computing and quantum-inspired algorithms, especially for optimization, for solving optimization problems. The talk will be in August, on August 20th at 6 p.m. So this time, this will be Thursday. So I hope you will. I hope that everyone will be able to attend as well. But the attendance today on Saturday was very good, so I'm very happy with this. And I hope that in our next episode you will also join. So with this, I would like to stop. So I thank once again Jacob for everything, for this talk and the discussions, and we thank everyone for the questions and participation, the active participation in this meetup. I will now stop recording, so we hope to see you next time.
Thank you.
Okay, I can see some next. I stopped recording, but I just want to check the final comments. Yeah. Okay, so I think that's all for today. So have a great weekend, everyone. Jacob, thank you once again. See you next time.
Thank you, Pavel.
Bye bye.
Okay. Bye.